Okay, hello. My name is Eric. Today I'm going to be presenting here webinar DEFLEXIO real-time IoT deformation sensors. Today I'm going to present with Richard, and in the following slide you will see his picture as well, and just in a few minutes you will see him also in a video feed. So today's agenda is to talk about sensors, but agenda will be later on. So today is going to be speaking me. My name is Eric Svitos. I'm an MBA, also PMP certified project manager. I have a background in civil engineering and experience with the IoT devices in the construction and also related to BIM world as well. And here with me today is going to join also in here, sitting in this spot in about 5 minutes, Richard, which is master's in electronic engineering and currently to be doctor in computer science, with experience in hardware and software design and development on variety of different sensors. So today's agenda is to give you a short introduction, then following with the technology overview, which is going to be handled by Richard, and giving you a summary of the technology, how we can apply it, and etc. In the end, we're going to hold a Q&A session, during which we will answer your questions asked during the webinar, as well as ask questions during the Q&A session. So we encourage you to ask questions as much as possible, and in case you're not going to have time to do that during the webinar, you're open to send us an email, which will be provided in the end of this webinar. So I'm going to start with the introduction. So first, who we are. So first and foremost, we represent the Institute of Electronic and Computer Science. And it is worthy to note that this is most highly ranked institute by international experts in area of electronics and computer science in the country. Here you can see our picture. We have quite big premises. Even more if you look behind the picture. Anyway, main research directions are extremely precise event timing, remote sensing and escape, space data processing, robotics and machine perception, signal processing and embedded intelligence, and smart sensor IoT devices, which is something related to this technology we're going to speak today. It is worth noting that we are collaborating with many global companies. As you can see, there's many logos, and from which most recognizable could be Philips, Volvo, Siemens, Airbus, and there's actually even more logos which we couldn't fit into the screen, but we chose the ones we work most actively with. So this shows sort of credibility that we're actually dealing with serious matters. This technology today we're going to be presenting is developed by Institute of Electronic Computer Science, as you already know, as part of Deep Tech Commoditization project, which is co-financed by Investment and Development Agency, which means that we have a specific funding over the period of 2 years, during which we work quite hard to develop this technology, which we're going to present soon enough, going a little bit more deeper. So basically, the technology is DEFLEXIO, which we have branded it, and the brand and the technology has developed from the institute where we actually right now, obviously. So why now? Why the technology is developed right now? Why we actually put emphasis on it? So what we have realized during the research, that currently retroactive methods for monitoring buildings and engineering structures are commonly used. And companies quite often are lacking the methods that would allow getting live data, live information about deformations in the structure. So this is the thing that we actually couldn't find alternative technology, and currently many companies rely on static, and you can see from the picture from just to get that idea of the traditional technology. So further ado, I'm going to give floor to Richard. He will continue speaking and giving you technology overview. Now I will gonna be back with the summary and Q&A session. Yeah, Richard, we're gonna switch seats.
Yes, thank you very much, Eric, for a brief introduction. My name is Richard Staturs. I'm a researcher here at Institute of Electronics and Computer Science, and I have been working with the development of this technology from the early beginnings, from the early project. And I will give you a brief introduction about the technology, how it works, what are the main parameters of developed prototypes, also give insights about testing we have performed in laboratory and field tests. So what is DEFLEXIO technology? The DEFLEXIO technology is a sensor system consisting of multiple interconnected sensor nodes that provides real-time continuous remote structure deformation and vibration monitoring. The main component of the system are the sensor nodes that are attachable to critical parts of the structure and give periodic information about the state of the structure. This allows to take proactive steps if significant deformations are detected, thus reducing risk of significant damage or degradation of the structure or even collapse, thus saving saving a lot of money. This kind of technology is installable to engineering structures such as bridges, buildings, and tunnels. And this kind of technology is relevant for construction engineering companies, engineering structure maintenance companies, or engineering structure surveyors. The origin of the technology is the first developments were done during national research program, where we developed technology that we call 3D shape sensing fabric. It consisted of sensor nodes that are embedded into wearable fabric and that allowed, by using sophisticated data processing algorithms, to reconstruct the shape of this fabric. This technology was developed for scoliosis treatment applications, where we developed prototype where wearable shirt consisting of this fabric, and by sending the sensor data to the smartphone, we could detect deviations from healthy posture, and if serious deviations were detected, a sound or vibrational feedback was given to the user, so the patient could be reminded to take a healthy posture. Using this technology, we applied for funding within Latvian Investment and Development Agency commercialization program, and were successful of getting this funding. And during this program, first 6 months were intended for feasibility studies and commercialization strategy development. And during these first 6 months, we identified new interesting application area, which is engineering structure deformation monitoring. And we thought that our technology could bring value to this area. Because of the reason that medical devices require very intensive and long medical clinical trials, that wasn't feasible for duration of this kind of project, we decided to adapt our technology for this new area. So how does this technology work? The main component of the system are sensors. Sensors, we're using accelerometer sensors that measure acceleration. By attaching these sensors to structure, it allows for us to measure vibrations. Another feature of accelerometer sensors are that in static conditions, when there is no acceleration, they measure acceleration due to gravity. By measuring direction of the gravity vector relative to sensor reference frame, it is possible to measure orientation in global reference frame. By attaching these sensors to various parts of the object or structure, and by combining sensor data using sophisticated algorithms, it is possible to reconstruct full three-dimensional shape of the structure. By measuring in various time intervals, it is possible to monitor how the structure changes over time on dynamic measurements. As accelerometer sensors, we're using micro electromechanical system or MEMS technology sensors, and the structure can be illustrated in with this simple diagram. The main component is ethylene mass that is attached to springs, and when there's no acceleration on the system, it measures no acceleration, and the measurement can be calibrated for zero measurements. When we apply acceleration to this system, the ethylene mass deviates from the rest equilibrium, and by measuring this deviation, it's possible to measure the acceleration. This deviation is linearly proportional to the applied acceleration. This kind of structure allows measurement of acceleration in single direction, but combining these structures in three perpendicular directions, it is possible to reconstruct full acceleration in three-dimensional space. This kind of structure is integratable in integrated circuits using MEMS technology, and there are commercially available sensor chips that are relatively low cost, relatively low power consumption, and for example, they are mostly nowadays used in mobile phones to detect the orientation of the phone to adjust the screen orientation. Particularly, we're using commercially available Bosch BMA 456 sensor that provides low temperature drift. To realize this kind of approach in real life, there comes two main challenges. The first challenge is how to connect a lot of sensor nodes in one system to gather the data from these sensor nodes to achieve high accuracy and provide complex measurement of objects with complex shapes. The second challenge is how to process this accelerometer sensor data to get meaningful information that would provide us with deformation information. To overcome these challenges, we have developed two novelties. The first novelty involves novel IT architecture for sensor node data acquisition that involves architecture, hardware, and software development. And the second innovation is data processing algorithms for shape reconstruction. For connecting multiple sensor nodes, we have developed energy efficient sensor communication solution that provides wired sensor connection with minimum number of wired connections. Between each sensor pair, only 4 connections are required, 2 for power transmission and 2 for data communication. We chose to develop wired sensor communication solution because wireless transmission is less energy efficient, and also each sensor node would require some power source, for example, battery, which would mean that the battery would need replacement, which is inconvenient for maintenance reasons. And our developed solution allows connection of several hundred sensor nodes and provides synchronized data acquisition. Here is illustrated overall architecture for the whole system. The yellow blocks are the sensor nodes that are connected using our developed communication solution. The sensor nodes are connected to central sensor hub. That main task is to provide central data access point for the sensors, and also provide electric power distribution to the sensor nodes. The sensor hub is connected to electric power source, such as electric power grid. Sensor data can be accessed locally through Bluetooth connection or through local area network. This data can be sent directly to monitoring computer. Also, data can be sent remotely using internet connection, either through Ethernet, Wi-Fi, or mobile network. where data can be sent to a central server, and data can be accessed from anywhere in the world from regular desktop computer. To test this approach ability to work in real environment, we have developed various proof of concept prototypes. And here is a list of the main parameters of these prototypes. The inclination accuracy error for the individual sensor nodes is less than 0.5 degrees, which provides accuracy with deformation measurements about 3 millimeters for 2 meter long structure. It allows connection of several hundred sensor nodes, provides deformation reconstruction in real time up to 100 times per second. It allows us for vibration measurements, but if only deformation measurements are required, then this can be reduced to 1 time or per second, or one time even per minute to save networking bandwidth. Sensor nodes provide very low power consumption. One sensor node consumes less than 1 milliampere. 1 milliampere. The sensor nodes are retrofittable to existing structure using either adhesives or using screws. The system provides remote data transfer using internet with either Ethernet, Wi-Fi, or 4G network connection. And currently we have developed 2 types of form factors. One where sensor nodes are integrated into humidity resistant casings and sensors connected with cables. Another form factor involved where sensors are integrated in flexible printed circuit board strip, similar to light emitting diodes strips. To test our prototypes, we have performed various laboratory tests to test the accuracy and ability to perform in various changing environment conditions, and also to test the ability to work in a real environment. We have performed 3 field tests. The first field test was done on shopping center rooftop. The second field test was done in bridge loading tests in railway overcross, and third test was on deformation measurements on spectator stands. So for accuracy tests, we attached our sensors on the 2 meter long structure, and by applying various weight loads on this structure, we measured various corresponding deformations. As ground truth data, we used Lade's distal laser meter, and from the test we got obtained that the maximum difference from the ground truth data was approximately less than 3 millimeters. To test our system's ability to work in changing temperature conditions, we performed tests with 3 different manufacturer sensors, such as ST, Bosch, and Freescale manufactured sensors. The temperature range tested was from -5 to 25 degrees Celsius. And during tests, we identified that the sensor nodes from Bosch was with the least amount of variance, achieving less than 5 micro values variance. Previously, we were using sensors that were without any temperature compensations, and the stability was more than 100 times worse. So during these tests, we found a very good solution for temperature stability. Also, various use cases require that sensors can work in very humid environments. We have experimented with various prototypes of casings, how to protect the electronics of the sensor nodes. The first tests were done with 3D printed casings, but we concluded that 3D printed material has small pores that provide very bad insulation from humid environment. So we also tested some existing casings from molded plastics, and they were very good, showed very good resistance to humidity. The temperature and humidity tests were performed in climate chamber that's available in our premises. The interesting fact is that this equipment is used for other team for testing equipment for Space-related applications, for example, they have developed a unique technology for very precise timing measurements, providing 1 picosecond accuracy. And this technology is used for satellite ranging, and they're very important to test their equipment in very extreme environment conditions. As I mentioned before, we have performed also a field test to test ability to work in real conditions. The first field test was done in shopping center on Spice. Spice shopping center is located in Riga, and one interesting feature is that they have very large area of flat rooftop, which is problematic in winter time when there is a lot of snow. And to ensure that the structure is safe, the snow must be cleaned from the rooftops, which is very expensive. So they are interested in system that could monitor the snow loads. For particular shopping center, they installed Rookie Smart Rooftop, and this company also already provides monitoring solution, but it only provides for the rooftops of this particular company. So we were interested if our technology could also measure these deformations. So we installed our sensor systems for duration about 2 months, and during the time we could get the data without interruptions. But the main conclusion from these tests were that the sensors used at the time had very high temperature drift, which forced us to go back to the laboratory to test and find sensors with less temperature drift. The second field test was done in the railway overcross in Daugavpils, where we installed our sensor nodes on 15-meter long bridge segments, and we installed a total of 11 sensor nodes. We were using also solar high accuracy Accelerometer sensor to provide ground truth data. Also, professional company Engineer Bove participated with conventional measurement methods. This company provides engineering structure inspection service, and during tests we got quite good correspondence with our ground truth data, measuring deformations that are from 0.5 to 0.15 degrees, and also our results agreed with the professional company's measured conclusions. One of the main takeaways from these tests were that our system is quite easily installable. It took for us about few hours to install our technology, while this professional company with conventional methods took a full day for setting up their equipment. The third field test was done on spectator stands in Biķernieki racing track during World Rally Cross event this year. The maintainer of this racing track was concerned about the integrity or the state of this old, nearly about 60 years old spectator stands, and we decided to try to install our sensor system to measure if there are any deformations during racing events where the spectator stands are filled with spectators. During these tests, we didn't measure any significant deformations, but the main takeaway from these tests was that the system withstood very harsh environment conditions. During duration of 1.5 weeks, it was quite bad weather with a lot of wind and high rain, and our system worked fine without any data interruptions, and the data could be remotely sent to our institute, where the server of data acquisition was installed. That's it about the technology, but this technology, as I mentioned before, is developed in Institute of Electronics and Computer Science with the help of our team. The team mainly consists of hardware and software engineers, as well as a digital signal processing algorithm expert, and to drive the commercialization. Also, we have several people that are involved in and with experience in area of commercialization. I would like to thank you for your attention. This concludes my introduction about my technical part about this technology, and I want to give word back to Eric to conclude this presentation and inform about next steps, and I will be back for the Q&A session as well. So yeah, Eric, the floor is yours.
Thank you, Richard. Yeah, so I'm back. Yeah, it's quite interesting. Thank you for presentation, and you can see the technology actually is quite revolutionary in terms of measuring live data compared to traditional way of doing so. It's quite impressive, given that also I'm from structural engineer myself, and I haven't been encountered with similar technology. So we are really proud of it. And yeah, the team also we have even more people behind us. We have people who are taking care of this webinar in the background, and other people. This is just the main researchers, the brains behind this yeah, great idea and implemented idea in the practice. As you noticed, there was several field tests, which is it's always complicated to testing in the field. It's not just a laboratory. So it was great experience for us, and yeah, we get many really good feedback. So yeah, so I'm gonna summarize what Richard told and I told in the early beginning. The main idea that the system core capability, what we see is to provide real-time data about deformations and vibrations from sensors which can be installed on linear elements and also can be covered on top of the surface and measure deformation and vibrations. And our competitive advantage actually consists of 4 main elements. Of course, the first element is the most critical, which is shape descriptive algorithm, which we have customly developed and which enables us to interpret data from different type of sensors, enabling system to be affordable and scalable. We have developed a specific IT system architecture in order to support this technology so that it would work in practice. Sensor communication solutions is unique because it allows to connect several hundred of sensors compared to other systems which typically connects 1 or 2 sensors. And in addition to that, we have developed custom hardware-based software in order to control sensors. So not only conventional, but also in hardware level. We have identified many different use cases. You see from the Richard presentation, we use it in the bridges, on the rooftops, and on the spectator structure. But there are many different other applications where we can use this software. And we have divided in 2 main segments. And of course, the third segment, which is other use cases, which is limited only to your imagination. So first and foremost, you can use this technology for monitoring. You can monitor bridges and viaducts. You can monitor buildings, either it's high-rise buildings, new buildings. It might be historical buildings which are close to collapse, which you would like to monitor whether the deformations is in a decent level of limits. And in case you see that limitations are exceeded, you get the live data about it, and you can be sure that you will react proactively rather than reactively, which means that the structure can collapse. You can also monitor industrial facilities. You can even monitor ground slides. If you live in an area where there's mountainsides, and ground slides might give you the risk of damaging the road, damaging the cities, and etc. Also, you can use sensor for preventive maintenance. You can make sure that the snow load doesn't impact the roof so that it exceeds limitation for the deformation. You can monitor live load, meaning you can see whether how the load from the storage units impacting the slabs, beams, and see whether you should react on it, or maybe you should reduce the load. You can monitor people load, meaning that in case there's some concert or public event, if people start coming in and in, you can see whether the deformation are not exceeding the limits, meaning you can save actually lives. You can monitor also prevent from traffic load and also seismic load, meaning that during the seismic activities, you can maintain the structure in a sense that you can be proactive when noticing some deviations from the over exceeding deformation. And of course, there are many different other use cases where we can use this technology. In general, you can use the technology everywhere you need to measure 24/7 deformations and vibrations. So the application can be wide range. It depends, of course, on the company, on the field you're working in, on the practical need you actually have. So we come to the point when we have to move forward. And we have to ask the question, what next? Because we Institute of Electronic and Computer Science, our next step is to make this technology available to the public market. And if you are interested in obtaining this IoT technology, feel free to contact us to discuss technical specification, because on 7th of December in 2020, quite soon, we will hold an official auction. So don't hesitate, feel free to contact us, write email or call directly to us, ask any questions you want. You can arrange private sessions with our researcher, with the team, to clarify specific things you are interested in, so that you might continue on using this technology further in your commercial application. Okay, with this, we are concluding all of our presentation, and we would like to turn to the Q&A session. And and Richard's going to join us. So we see that a couple of questions we have. So I'm going to read questions out loud, and I hope you can see both Richard and I. And first question is, how are you planning to apply it in a building for monitoring loads in residential area? I guess the main idea behind monitoring using sensors for residential area is to either cover beams or cover, here it is. Okay. So basically in the residential area you can there's typically a beam and there's typical and slabs. And actually what we did sort of field test also in our institution, and Richard may also share the outcome. But what we did, we actually do cover our sensors put them on the beams in our institute, and we do cover them also in the column, because the column can go can kind of shift from left to right, and we also can monitor and measure these kind of things. And I don't know, could you share something how you did in institute, because this is basically the residential area we are right now.
So as I mentioned before, we currently provide two installation methods. One is with adhesives and one with screws. And in institute premises, we used adhesives, and they could withstand for like more than a month. The sensors were able to withstand this duration. I think,
So this was the fourth sort of field test which we also did, and so it went well. So there's a question regarding how it withstands temperatures, and well, basically we mentioned that we actually we see that, of course, we haven't had a chance to test it in -20, and maybe Richard can copy, but we feel that they are quite withstanding with them. Yeah.
Yes, no, currently we tested only temperature range from -5 to 35 degrees, but the sensor components can from the technical specification can withstand even higher temperature range, and if it's relevant for some application, we could test it further.
Okay, yeah. Yes, so I see that next question is regarding how you're planning to make it available for commercial market. Yeah, so our idea is the main idea behind sort of putting it and make it available to you to use it is acquiring license from institute, because obviously we are researching institute. We are not here to use it and apply it, but we are here to test it. And one key factor which we'd like to emphasize is together with the license, we can also embark in a journey together with you in order to develop and apply this technology specifically to your use case. Meaning that we can even fine-tune the specification currently in a software to see how it fits into your needs. Because you might represent construction company, you might represent bridge monitoring company, you might represent maintenance company. And for all of those companies, there's specific needs. It might be that you are somewhere in Canada seeking to monitor snow. Yeah, in Canada there's so much snow. So yeah, so basically, and for that, of course, there's a little bit more specific than say that you would like to monitor some deviation from vertical point in high-rise buildings. Obviously, there's many different use cases, and together with license, we can embark on a journey with you, with your internal R&D department to find the best fit to your need. Okay, I can see that we actually have no more questions. Maybe if anybody else have some questions, feel free to ask. And in any case, yeah, if you have some questions, I'm gonna put on back one slide to emphasize it. Here's the email, here's the phone number. Feel free to follow us. We have a webpage, deflexio.com. We also have a webpage of Institute of Electronics, which you can generally just Google it. And yeah, feel free to ask questions. Make sure that you are till 7th December. Contact us, and yeah, hopefully we can develop something worthwhile. Okay. Yeah. Thank you, Richard.
Yes, thank you very much for your attention.
Yeah. Thank you, everybody, and have a nice rest of the day. See ya.
See ya. Stay safe.
Yeah. Stay safe. Bye.
Goodbye.